hope so. Maybe.
Or no.
No, they use for and brings it.
What is N?
But like.
Math comes clear.
Yeah, that's.
Yeah, you could, I thought I did it.
I just, I don't know, I think I'll say it's different for your angle.
Yeah, that's. Like, it's not like.
You might have got the same thing.
Well, never like, you know, it's not. It's not.
I just wanted to do It's a hard one.
Wait, maybe I got 160 right.
All right,
160 times 2.
just want to finish talking about error bounds.
I just know that's the concept.
With error bound, we talked about how we can find a safe estimation of the accuracy of our partial sum if we look at the first unused term in the series. Now, the first unused term in the series is not going to give us the exact error, but it will give us something that we know it can't be any worse than that amount. So page 2 here is to determine the number of terms required to approximate the sum of the series with error less than 10 to the negative 3, which is 1/1000. So way we can do that is, well, we know that this is true, right? S minus S sub n absolute value of is less than or equal to A sub n plus 1. Again, this means that whatever the difference is between the actual sum, which most of the time we're not going to know, versus the partial sum, either the S sub 4, S sub 5, whatever. In this case, we're trying to figure out where is that difference where our accuracy is going to be, it's going to be less than or equal to, in this case, we want the accuracy to be less than 10 to the negative 3. So we can do this. We can ask ourselves, well, what will make the first unused term, if I remove the alternator, it's just basically 1/n plus 1, right? Because 1/n is the current term, whatever that current term is, and whatever n plus 1 is the first unused term. When is the first unused term in my series going to be less than 1/10 to the third, or 1/1000? Okay, and we just basically solve this inequality here. Okay, so we solve this inequality here. I can say n plus 1 is greater than 1000. So if I solve for n, I'll get n is greater than 999. So if n is greater than 999 terms, our partial sums approximation is off by no more than 1/1000. Okay. Okay. So that's really the a lot of these problems that what we're doing is we're just looking at the first unused term, and that is giving us the error of the current partial sum. Okay. All right. Any questions from any of these homework and classroom problems? All right, so today we're going to start looking at 10.10. Now, the reason why you're going to see in our set of notes here, they're kind of jumping all over the place here. I'm trying to match the notes that I have with the sections in the book, so that's why it feels like we're kind of jumping here, but I have all the notes in the order that we're covering them, so hopefully that won't be too difficult here. So some of the some of these sections we're not finishing until the following day or the day after. So sometimes the AP practice problems are not assigned until we fully finished that section in the according to the book order. But we have a few more sections to go. We have lessons today, and then new material Monday through Thursday, and we can start our test review next Friday. So today is about Taylor polynomial approximations. So let me just go through some of the notes here. So a Taylor polynomial, they're created in order to help us approximate other functions. Other functions meaning something like sine, cosine, natural log, rational functions, exponential functions. So these are going to be the common ones that we're going to be using Taylor polynomials for. So the idea is that, why do we do this? Because polynomials are easier to work with in calculus than these other types of functions. And what we mean by easier is in terms of the derivative, because the derivative and integral, it's pretty easy with polynomials. We're just always either adding one or subtracting one. With sine and cosine, natural log, it's a little bit messier, right? Especially find the second and third and fourth and fifth derivative. It's just not as clean. It's not as fast as polynomials. We also have something called a Maclaurin polynomial. It's basically the same thing. It's a special type of Taylor polynomial. It's centered at x equals 0. Taylor polynomial can be centered at other x values, but Maclaurin polynomial is always centered at 0. So to start, we choose an x value to center our polynomial. So let's call that center C, x equals C. Our approximation will have the same y value as the original function as x equals C. So that's one way that we can build our approximation. We're basically going to be expanding out. So let's say our C value is here. And the easiest approximation that we can make is at that point. Now, if I just have that point there, it's not a very good approximation of this curve, right? Because anything outside of that point, I don't have any of the data to work with. But if we can gather more information about the function that we're talking about, then we can start building polynomial function that will begin to mimic and mirror the function that we're trying to make it look like. So we expand the approximation about x equals C. So basically, we're going to be the more information we gather, the more our polynomial is going to begin looking like the graph. But it's going to be, wherever the center is, it's going to start expanding the similarities from that center in both directions. Okay, yeah. So another way of saying this, the function is centered at x equals C. So past the point, we can look at a linear approximation, right? We've been doing linear approximation. So for instance, let's say f of x equals e to the x. Okay, we know that f of 0 equals 1, right? If I plug 0 in for x, I get 1. And so we need p of 0 to equal to 1. So we're going to shift over to this function that we're going to, because this is a polynomial here. We're going to actually shift over to this e to the x here. We're going to try to create a polynomial that is going to look like this e to the x. Okay. But we're going to start centering at 0 in this case. So here at 0. Okay. let's say, so we have the same points. The order pair is just 0, 1 between this new graph and this polynomial that we're going to build. And next, we want to make the slope equal to each other. So let's find f prime. And let's find f prime of 1. So what's e to the x's derivative? Yep. And then if I do e to the, or if I do f prime of 1, that's just equal to e, right? So I'm sorry, not 1, my bad. F prime is 0, because we're talking about x equals 0 here. So f prime of 0 is equal to what? E to the 0 is 1. Okay, so that's my slope. So if I can create an equation with the same slope and the same point, then that's just a linear function, right? So we want f prime of 0 to equal to p prime of 0. So now our Taylor polynomial will just be a linear equation if we're just matching the first order. So y minus y sub 1 is equal to m times x minus x sub 1. My order pair is 0, 1. My slope is 1. So my equation, y minus 1 is equal to 1 times x minus 0. Y is equal to x plus 1. Right. Now, if we look at just that x plus 1, this is what the graph looks like here. Y-intercept of 1. So, I mean, if we're close to our source of our center, then the linear approximation can probably do a decent job of approximating, but it's not adapting to the curve at all. So it's not a great approximation, right? Once we extend past 0, then our approximation is getting a lot worse. Okay. So we call this a first order approximation because we're just matching the slope at that point. That's it. It works for a very small interval around that point of the center. So what if at that center, we not only match the point and the slope, but we also match the curvature, second derivative, the concavity, and then we keep going, the third derivative, the fourth derivative, fifth derivative. And if we keep going, the idea is that this polynomial is going to gain more and more information about this exponential function e to the x. And it's going to begin to look more and more like e to the x, the more information we give it. So the idea is, the more that this polynomial can match up with the function in terms of its order pair, slope, concavity, third derivative, fourth derivative, fifth derivative, it'll begin to look more and more like that graph.
But with this method, you can never get it exact, right?
Well, for the ones that we're going to deal with, there is a certain pattern that's going to come up. So technically, if we have that pattern that is that's repeatable and a pattern that is easy to identify, then we can technically say, okay, as n approaches infinity, this infinite series will eventually look exactly like the function that we're trying to build, technically, right? But right now, we're only talking about this Taylor polynomial of a certain degree. So it's only going to, right now, it's only going to match up to a certain point. Okay. So I just want to just do a quick demonstration of this. I don't want you to write anything down yet because we are going to explore this in full, but I'm thinking maybe this will be a good way to help us see a big picture of what's going on. Right. So I want to switch over to a Desmos graph that I have just to show us here. Give me a second. Okay, so no need to write this down. I just want you guys to look at this right now. Okay, so this is what e to the x would look like if we were to take the polynomial function and build it around that e to the x. So it looks like this. It's 1 plus x. We're going to look at this in more detail, but right now we can tell that it's a polynomial. This polynomial is built in a certain way where it's going to mimic the information about e to the x. Okay, so this is what I want us to explore. Okay. Now, let me show you from a graphical perspective what's going on. So let's say we are just doing first order. So if you look at e to the x and 1 plus x, obviously it's not very good, right? I mean, it is, if we're really, really close to the center, then it's a pretty good approximation. But then once we get past once it starts curving, well, we're not getting a very good approximation. But what if we're able to add information about the slope and match the slope, or not slope, the concavity with that of e to the x, then it would be looking like that x squared over 2 factorial. So let me switch over here. You can tell that this parabola is doing a better job of matching with that e to the x. Obviously, it's not perfect, but it extends a little bit further than before, right? And then if you were to match the third derivative, okay, that's what this x cubed is doing. Let me show you what that graph looks like. And it's doing an even better job, right? Obviously, once we get past this point, but it's even up to 3 or 4, it's still pretty close, right? It's still kind of moving the same direction there. Okay, so this polynomial is built up to the 5th degree. So let me show you what the 4th degree looks like. Okay. Extends even further, even though this left side is completely not in a great approximation on this side, but you can tell that it's getting better and better, right? Even all the way up to here, it's still pretty close to each other. Okay. And finally, 5th degree. Okay, I only built this polynomial up to the 5th degree, but if you look at the 5th degree here, past in the negative region, it still needs a lot more work here. But in the positive region, if you look between the red graph and the blue graph, it's virtually identical up to a certain point. Even like going all the way, we're not even seeing the distinction between the two of them until we get past getting close to 5, right? Even then, it's really, really close to each other. So the idea that they are matching in point, slope, concavity, third derivative, fourth derivative, fifth derivative, and it's the more information you give it, the more that polynomial is able to match with the look of the graph it's trying to imitate. Okay. I'm sorry.
Where'd you get the factorial?
Right. So the factorial is part of the formula that we're going to build, and I want to kind of show us, why is that factorial there? So let me give you another detail about that. Let me switch back over to. Okay. So this is what I want to show you. Again, don't write anything down yet. We're going to get into all this step by step, but just want to kind of give you some big picture idea here. So we talked about how this polynomial to the 5th degree is going to do a pretty good job of matching that e to the x up to a certain point. But I want to show you and prove to you that the function and this polynomial is actually going to match all their derivatives up to the 5th derivative. Okay, and the factorial, the interesting thing about the factorial is that it's kind of like a timer. It's kind of waiting for the appropriate time for that derivative to show up with the value that it's doing. And I want to show you what I mean by that. So if I want to find f of 0, right? F of 0 is just 1, and p of 0 is also 1 because all the x's goes away, right? So the order, so the order pair is the same, right? At 0. Okay, we picked e to the x. It's an easy function. It's not a messy derivative, and it's always, we can kind of just focus our attention on the right side here. We know f prime of x is going to be what? Just e to the x. And the derivative of f prime of 0 is still going to be what? still gonna be 1, right? So if I were to take this function, if I were to find the derivative, okay, let's go down this list here. So if I were to find the first derivative and then find p prime of 1, the 1 goes to a what? And then x becomes a 1. Okay, what does 1/2 x squared become? X. What does 1 over 3 factorial x cubed becomes? Good. So that 3 factorial is waiting for that 3 to come down to cancel out, and it's going to come down to a lower degree. So this is what p prime looks like, right? We're just going through power rule, but you see how the factorial is kind of waiting for that term, and then once that cancels out, then it's down to 2 factorial. This will go down to 3 factorial. This is go down to 4 factorial. So this is not going to kind of show itself until it's the right time. But if I do p prime of x, this is the cleaned up version. We see the 2's cancel out. We see the 3's cancel out. We see the 4's cancel out. That 4 factorial turns to a 3 factorial because the 4's cancel out. And then the 5 factorial and the 5 cancels out to be just that 4 factorial. Does that make sense? We're just doing power rule here. Okay. So now what would happen if I were to do p prime of 0? P prime of 0 is equal to what? Because all this goes to 0. So this matches up, right? P prime of 0 equals 1. F prime of 0 is equal to 1. Okay. So now let's find the second derivative. What's the second derivative of the function that we're trying to imitate here? F prime of x is still, F prime of x is still what? Still e to the x. The derivative at 0 is still going to be 1. Okay. So if this is doing a good job of matching that derivative, it should also produce a p double prime of 0 being 1. Well, here's p double prime of 0, right? We can just find the derivative again. 1 goes to 0. X becomes 1. Okay. This cancels out. The 3 factorial cancels out. 4 factorial cancels out. So now my p prime is just, p double prime is just 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed. And then if I do p double prime of 0, what's going to happen to all these x's? It goes to away, and it matches perfectly with p double prime. The concavity value is 1. Right? And then we keep going, right? Third derivative, fourth derivative, fifth derivative. It's all going to be 1 because f of x is just always going to be an easy function. And if you look at the rest of this pattern here, the third derivative, right? The 1/2 x squared becomes just x. The 1 over 3 factorial x cubed, the 3 comes down. We just do power rule here. We're just left with 1/2 x squared. P triple prime of 0 is still 1. But the x and x squared, they're going to come into play, but it's not going to show up until we do the next derivative. So if I do the fourth derivative here, 1 becomes 0, x becomes 1, 1/2 x squared becomes x. If I do the fourth derivative at 0, I'm going to end up with 1. So that matches up with the fourth derivative. And finally, the fifth derivative, 1 plus x just becomes 1. And so the reason why the two graphs is able to do, why this polynomial is able to do a pretty good job of matching with this function is because it's matched stride for stride with the function up to the fifth derivative. Okay. And I just want you guys to see that the factorial is kind of doing its job, right? It's not allowing the x to show itself until the degree is ready for us to evaluate, right? So that 5 factorial is basically allowing for this fifth derivative to work itself down all the way to the constant, and then it's going to take away the coefficient along the way. 5 factorial, 4, 3 of 3, 2 and 2. Okay. All right. So just want to give a big picture. I know there's still a lot of confusion here, but that's what we're working towards, that we're going to be building these polynomials in the sense that we're going to make this mimic the behavior of the function. The way we do that is we match derivative values, second, third, fourth, fifth derivative values. Okay. All right. So let's look at how we can build these Taylor polynomials. So if a function is differentiable, is a differentiable function, then an approximation of the function centered about x can be modeled by, and we're assuming that this function is non-polynomial, like sine or cosine or natural log or e to the x. And then the p is representing that this is a polynomial, and the n represents that it's a polynomial of the nth degree. If it's p sub 3x, that means it's only going to be matching up to the third derivative of that function. But here's how we can do it. We're always going to be matching the points. And then we're going to be building the tangent line equation. So that's just f prime of c times x minus c. And then we're going to start building our second derivative. So we're going to match the second derivative from the function over 2 factorial. And that 2 factorial is going to allow for the derivative to kind of match with that factorial until it's ready for it to show itself. And then we have x minus c to the second. And that c is where you're starting to build, match up the graph and the polynomial. It can be at 0, but also we can also start building the connection between the graph, or the anchor, basically the anchor between the polynomial and the function can start at any c value. It could be starting at 2, could be starting at -2, could be starting at 5. So, but all that will be provided for us. We're never going to have to guess where the center of the polynomial and the function is going to be. Okay, and then the pattern keeps going. We want to match the third derivative at that center over 3 factorial x minus c to the third, and we just keep going depending on how many degrees we want to match or how many degrees the problem is asking for us to pair up with. So here's the general formula. It's the nth derivative evaluated at the center over n factorial. We saw that the factorial is doing its job of making sure that it's going to be there when that derivative is taken, so that it doesn't disappear. And then we have x minus c raised to the nth degree.
So if you take the n to infinity, you get the exact.
You get the exact, yeah. Now, a Maclaurin series is where the center is always about 0. So Taylor polynomial has more flexibility. It can build the connection starting at any c value at any center, but Maclaurin series, we call Maclaurin series if we want to just always, if we just want to build the connection point at 0. So so it's just f of 0 plus f prime of 0 of x plus f double prime of 0 over 2 factorial x squared. It's a little bit cleaner because it doesn't need that x minus c, because that c is basically 0. So essentially, they're the same formula. It's just Taylor formula looks a little messier because it needs to adjust to the fact that it's not centered at 0, so it just has a little bit more involvement there. Okay, so let's try a couple of examples here. Number 1 says, find the third degree Maclaurin polynomial for the function e to the 2x. So basically, we want to find the first, second, and third derivative, put that information into the Maclaurin series so that the polynomial has that information and is able to match the function's derivative up to the third derivative value. Okay, so let's just play with that f of x here, so we can just gather that information so that we can actually put it into the formula. So let's find, so we know f of x is e to the 2x. Okay, what's f prime of x? Yeah, What's f double prime of x? Okay, yeah. We're just doing chain rule for these, right? And then next up, e to the u times u prime. Third derivative is 8e to the 2x. Okay, we're going to continue gathering information here because really we want the slopes or the derivative values at 0. And again, Maclaurin series, we should have to understand that is always talking about the center being at 0. And so we're just going to do f prime is 0 and all the derivatives at 0. So f of 0 first. E to the 0 is 1. What's f prime of 0? Yeah, good. 2e to the 0, which is 2. F double prime of 0, 4. Okay, so these are nice, right? Because the that 0 is going to wipe out a lot of the messiness here. F triple prime of 0, third derivative is at 8. Okay, so we're going to insert this information into the Maclaurin polynomial so that it has that information, so it's able to begin mimicking this e to the 2x because it's able to have the similarities between the two. At least only up to, we only care about up to the third degree because it's asking for a third degree Maclaurin series. Okay, so we'll do p sub 3 of x. So we only care about building a polynomial matching up to the third derivative. So we'll do f of 0. Okay, so just follow the formula here. F of 0 equals 1, right? So it needs to match the y value. So that's basically the anchor of our polynomial here. Plus, yeah, also wants to match the slope. So right now this is called a first order polynomial because it's only linear, right? But we're going to gather more information so that I can build the concavity and build the third derivative, build the curvature. Okay, next up, second derivative at 0 is 4. And that 2 factorial is kind of protecting it so that it doesn't completely go away. And so that's there too. It's like a timer to make sure that that third derivative or second derivative is not going to show itself until the time is ready. Times x to the
What's that?
second.
Okay.
And plus 8. Yep, 8 over 3 factorial x cubed. So if you were to graph this function, this is going to look pretty similar to e to the 2x up to a certain point, right? Obviously, the more information you give it, the more it's going to mimic that exponential function. Yeah, so this is our third degree polynomial, Maclaurin polynomial.
Clean it up.
But if we were to find p prime of x, p double prime of x, p triple prime of x, third derivative at 0, it's going to end up matching this exactly. And the 2 and 3 factorial are there to kind of help it make sure that it gets to these values at the appropriate derivatives. Right. So next up, it says evaluate f of 0.2 and polynomial 0.2. So basically, we know that these are not the same things. I mean, they're basically, this is trying to mimic this f of x. So if I were to plug 0.2 in here versus 0.2 in here, these should be pretty close, but they're going to be off because this is only an approximation of the f of x. But we can use our calculator. F of 0.2 is equal to e to the 2 times 0.2, and this is roughly 1.4198. Meanwhile, if I were to plug a 0.2 into the third degree Taylor polynomial, okay, I'll do this so that you guys don't have to do the math, ends up being 1.4906 repeating. So this is only an approximation, but it's doing a pretty good job. It's pretty close. So the actual y value is 1.4198 at 0.2, but the polynomial is going to be 1.4906 repeating. Obviously, if we were to add more information, 4th, 5th, 6th degree, then we can expect this approximation to be even closer or even more accurate relative to the exact value. Okay, so let's build another Taylor polynomial, and now we're going to be trying to make a polynomial imitate the information or the graph of natural log of x. And the way we can imitate the best is to gather information about everything up to the fourth derivative of natural log of x. Okay, so we're just going to gather information and then take all that information that we gather from all the way up to the fourth derivative and insert it into the polynomial for our Taylor series, or sorry, our Taylor polynomial. Okay, so we start off with f of x being natural log of x. Okay, what's f prime? X. Okay, I'm going to bring that x up to the top so that I can get it ready for the next stage. I don't prefer not to go through quotient rule here. Okay, f double prime of x. What's power rule there? -1x to the -2. Right, derivative, right? Okay, and then third derivative. Okay, so now this is not centered at 0 anymore. This is centered at 1. So this is not going to be a Maclaurin series. It's going to be a Taylor polynomial. But the only adjustment with this is that instead of x squared, x cubed, we got to do x minus 1 squared, x minus 1 cubed. That's really the only difference we're going to see. And the fact that we're not going to do f of 0. We're going to do f of everything prime, double prime at 1. Okay, so we're going to gather information to insert into our polynomial. So f of 1, what's natural log of 1? 0, okay. 1 over x, so 1 over 1. F prime of 1 is 1. Let me clean this up here. This is -1 over x squared. F double prime of 1 is equal to -1, okay. Let me clean this on here. 2 over x cubed. F third derivative at 1 is 2. Okay. So piece by piece, we're going to put them into the appropriate places so that this polynomial can do its job of imitating this natural log function up to the third degree, centered at 1. So we'll do p sub 4 of x, fourth degree polynomial. It's only going to be an approximation. We only have information up to the fourth derivative, but we start off with our y value, which is start off with what? 0, right? That's our because it's going to match the points. And then the next part is going to feel like just point slope form. So f prime of 1 is what? 1 times x minus 1. Okay. So this first portion is just, really just kind of building tangent line equation. And then after that, then is going to feel more like the formula that we're going to see with the factorials involved. Minus, what's next? Yeah, -1 over 2 factorial times, yeah. Plus, now at the third derivative. Yep. -1 cube, yep. Yes.
Are we missing the fourth derivative?
Oh, sorry. I didn't get to the fourth derivative. Thank you. I missed that part. Okay, so fourth derivative of x. What's the fourth derivative? Okay, thanks. -6x to the -4. -6 over x to the fourth. F to the fourth derivative of 1 is equal to what? -6. Okay, sorry, I left out one term there. So that last term is going to be minus 6 over 4 factorial x minus 1 to the fourth. Okay, so for your homework, you're just going to be kind of practicing using Taylor polynomial, but really you're just taking your function that's given to you, find the derivative up to the point of that degree, and then plug in the center, and then piece by piece put it into the Taylor polynomial or the Maclaurin polynomial. Okay, all right, come get your phones. Oh, it's a page I left out of the packet accidentally, so it's just, it should go after 2 and before 3, so I call it 2B in the packet. From basketball yesterday.